In this video, I want to show you a few of what I call my pro tips for solving problems like this, coming up with the equations for these graphs. The first one is that if you look at any of these graphs, this is the first one, and that's the same one that we've been working with, and you have the answer to that. That one there, the next one down here, this graph is the same for every student. It's a new graph for you, but it's the same for every student. So once one person gets it, you're welcome to share the answer with everybody else, but know that the process of working out the answer is really how you're going to succeed on these. So pro tip one is to look for this little magnifying glass at the bottom right hand corner of any of these graphs. If you click on that magnifier, it will actually increase the size of the graph. It'll give you a larger version of the graph, which makes it a lot easier to see where things are happening. It lets you zoom in on important places in the graph, and that becomes even more important, as you'll see in a minute, on graphs that are even more complex. So that's pro tip number one. Check out that magnifying glass and blow things up so you can really see what's going on. The next pro tip is something I want to call crossings. I want you to look for crossings on any graph. And this is a really good example of one. This graph looks like it has a little oval here, a larger oval here, and the biggest oval is outside all of them. It looks like three separate ovals, but it's not. If I grab just any point, I'm just going to start right here on this graph here. I'm going to go in this direction just because that's the easiest way to explain this. One thing that could be happening here is that the graph could be following this path where it comes down inside this little, on the inside oval, this medium-sized oval, and then stays on the path that is the medium-sized oval. But if that happens, then you're just going to be going around and around and around in a circuit that doesn't give you the whole graph. So that's not actually what's happening. Whenever you see locations like this where that could be happening, it's likely not. It's much more likely that the graph is coming down on this inside curve, crossing over through here somewhere, and then coming back out on the outside, right? Coming out here. So if I were here on the curve coming this way, I'd actually be more likely to be going that way, but it just sort of depends on where you start. Let's say I'm going this way. I'm on the outside curve. Chances are I'm going to cross over and go to the inside curve here. And then the same thing up here. I'm starting on this region up here. I'm starting on the outside. I'm going to cross over and go to the inside. So as you're tracking your X and Y values, keep that in mind. That's pro tip number two. Pro tip number three is something I call the failed loop. Let me see if I can find one that's got a nice failed loop for us. Don't see any there. Give me a second, I'll come back with a different set of graphs. Okay, this is a really good one. So let me blow it up, and then let me grab a pen so I can annotate. As I'm following this graph along, say I'm about down here, and I follow it along, and I come to this X value of, looks like about 2.5. First of all, I'd probably just call that 2 or 3. I'd pick one. And on this side, let's say I call this one 3. Because that's as close as you need to get when you're doing your initial graphs. Then I would call this one -3 because of the symmetry you see here. So let's say we get to 3, X comes down, comes up to 7, comes down as far as 3, and then it starts going back up again, right? Y, on the other hand, starts down here at -5. It goes up, and it goes up, and it goes up, and it goes up more slowly here, but it keeps going up. It just keeps going up, right? So this peak right here might be a failed loop. And by that, what I mean is, if you imagine that instead of a peak here, you have a loop, but in fact the loop failed, then when you follow your Y values, you're going to have, starting at -5, it's going to come up to about 3, then it's going to go down again to maybe 2 or 1, and then go back up again. And what that does on your X of t, or in this case Y of t graph, is that it's going to introduce an extra little bump in the graph. What the extra little bump in the graph does is gives you another very small leg in which to put an average, a midpoint. And that's going to make your graph connect in a different place than it would have otherwise. If you do that on this side, you're also going to want to do it on this side. Keeping your values the same, your up-down values the same for both parts of the graph when you get to them, because that symmetry still exists there. That will introduce an extra little bump in the graph for the values of Y. Even though X doesn't change, it comes down to about 3 and then goes back up again. Y, instead of coming up and continuing up, will go up. It'll come down just for a second, and then it'll start to go up again. So you'll get on your y of t graph, instead of having y just coming up and up and up and up and up, you would have, let me grab a different color here real quick. You will have an up and up, just a quick down, and then another up. And so there's another midpoint right here that you didn't have a second ago. There's a midpoint right here that when you connect your graph, you'll be connecting it through that midpoint, which you didn't have before. So that's my pro tip number 3. Look for what I call failed loops. If you find x or y is either just coming up and up and up and up in spite of what looks like it should be a change in the graph, then that's probably a failed loop. Pro tip number 4 has to do with how you actually enter your answers. I'm going to use this one because this is the one you know the answers for, and this will just help me demonstrate to you what the answer should look like at the same time. We know an answer to this one is 7 times the sine of t minus 3 times the sine of 7t. Not sure what's going on with that extra parenthesis there. I don't need that. In fact, I don't want that. And that's the x equation. And the y equation is 7 times the cosine of t. It's a plus instead of a minus. And then we have 3 times the cosine of 7t. This is a correct answer. It's not the only one. If you did this graph by yourself and found that you got different equations, but your graph still looked like this when you were done, then your answer is correct, and you will get full credit for it when I go through and look at these manually. So if your graph looks like this, then you're done. Even though you may not have right answers here, you may not have green boxes. I'm not sure why mine are not showing as green boxes, but they're not. If you don't get those green boxes, but your graph is completely covered like this, then it's correct, and you will get full credit for it. You'll just have to wait until I grade them manually. The thing is, I want to show you what happens if you were getting close, but you kept pushing and couldn't figure out quite what the right numbers were, and you started to try to find ways to kind of manipulate the graph, and you ended up using decimal values. You can see here that my graph is really close, but it's not bang on. So let's see what happens if I change this one to match it. Just submit it first. Right? It's not even, it's actually less close now. Maybe if I had 0.1 t here and 6.9 t here. The reason I'm doing this is because students often do when they can't, oh, that's a mess. They often can't figure out what an answer should be, and so they start trying to what I call brute force the problem, and that's just not a solution, right? Every single one of the answers here will have integer values here. So instead of a 6.9, I need to use 7. I'm going to try 7.1 and 2.9 in this other one, just to see if that can counterbalance it. So you can see it's really close, but it's not quite right. So my pro tip number 4 is don't use decimals here. If it's really, really close, first of all of the answers have integers here. They're all whole numbers. Okay, that's a 3, that's a 3, and that's a 7. So you won't get the green box. I guarantee you won't get the green boxes and the green check marks if you don't use whole numbers here. And when I look at them manually, I'm not going to give you credit either, because you're just trying to brute force the answer. The answers all have integers in these positions. There's a 7 there, a 1 here, a 3 here, a 7 here, a 7, a 1, that should be a 1t, a 3, and a 7. Those are all integers. Okay? Don't use decimals. That's pro tip number 4. I hope that's helpful. You may still have additional questions, which is absolutely fine. Use the project discussion to ask each other questions. You're certainly welcome to collaborate on this. Remember that everyone has different problems after questions number 1 and 2. So if you're collaborating, that's fine, and you're allowed to collaborate, but everyone's going to have different questions. So once you find the answer for one, you've helped student A helps student B with question 1, and student B should help student A with their question 1 as well. So feel free to collaborate, and also feel free to ask questions in the discussion if appropriate, or if I don't see any responses from other students. I may chime in the discussion and try to answer your questions, or you can just send me a message directly and I'll see what I can do to help. Have fun with your project.